Continuing on our exploration to find the right exponent for the Bill-James Pythagorean theorem, I have this little SQL query that Morris and I have written, and it's basically very similar to what we looked at before when we did our wins estimators SQL queries. So these will get put into the results table. We'll take all the data from 1901 and we'll dump this data table into our studio to better work with the data. So let's run this query. And here's our result. And we ended up with 2346 rows, which are all the team seasons since 1901. And we've got two new columns or field names here, wins ratio and runs ratio, and these are calculations based on wins divided by losses and runs to runs allowed. And better teams with higher winning percentage should have a ratio over 1 here. Their runs to runs allowed should be more than 1, and you can see that's the case here for all the winning teams. The runs is greater than the runs allowed, which is already here too. So we're going to download these results and move to our studio to run some code to find the exponent. Do a logarithmic transformation, then do a regression to find the right exponent. So here we are in our studio, and we have written some R code to help understand better this log transformation to estimate the exponent in the Pythagorean formula. So first we have to get the data from SQL Sandbox, and it's Lawman Sandbox 11 for me, and we should have a new data frame called Bill James data. Good, the right number of observations, 11 variables. Let's look at it. Year, team, runs against, it's all there, just like we saw it in the SQL Sandbox. Very good. So I want to do a little more algebra to convince you that we are going to be finding the right slope of the line, the regression line between our two log terms. So here's the idea. Remember what we've got. We've got wins divided by losses, and that's called the wins ratio. That equals the runs ratio called runs divided by runs allowed, and that's going to be squared. That term's going to be squared. That's the normal Pythagorean theorem. The question we want to ask is, what is the best exponent? So instead of using 2 here, I'm going to make that m now as an unknown. We're going to try to solve for m and find the right term here that's going to give us the best estimator here, the smallest estimator. So we do a log transformation, and the log transformation just takes the log of both sides of the equation. So log of the wins ratio, and we'll keep it wins divided by losses, but it's the log of the wins ratio equals m times the log of the runs ratio. So what we're going to do now is treat this variable as y. Y now is the log of the wins ratio. And we'll have m here, and the log of the runs ratio we'll treat as x. And if we have an error term in our regression, in other words, the intercept may not be right at 0. We may need an intercept term off of 0. This looks like an equation of a line. So we're going to fit these log ratios, the log of the wins ratio and the log of the runs ratio, to a linear model. And we're going to try to solve for m. And m is the slope of the line, the best fit line that we're going to do. So part of this, first thing we'll do is look at a scatter plot of the wins ratio to the runs ratio, see what it looks like, and then we'll actually do a linear model function of the log wins ratio against the logs run ratio. In other words, The log's run ratio will be on the x-axis since this is the x term. So this is where the log's run ratio will go. And over here will be the y term, and this is where the log of the wins ratio will go. And we'll get different data points for different years where these numbers are for the same year and fit a best fit line to it to get the potential intercept where it crosses the y-axis, and also get the slope of the best fit line. The slope here is going to indicate the best exponent for our set of data here. Now the key is we can do any data we want. We can just look at the 2000s. We can look at just the 1950s. Look at the dead ball era. Any era we want, we can put into this model to get the best fit line of the Pythagorean theorem. That's what this process will do for us, is find the best estimator for the exponent in this form of the equation. I'm going to clear this up and we'll run a scatter plot to look at the data. We're going to run a scatter plot now of just the runs ratio versus the win ratio. This is the data straight from the SQL sandbox. This isn't the log transformation yet. And you can see this is the runs ratio versus the win ratio. And you can see there's probably a best fit line here. Doesn't look super linear. Looks like there's a little curve in it. Not sure what that's about. But the x-axis has the runs ratio and the y-axis has the win ratio for all those team seasons. But we really are doing the log transformation of these two data sets. So we can find the slope of the best fit line. Let's run that. Now we've added two new variables to our data frame. That's what the with command does. We've added a new variable called win ratio log and another variable called run ratio log. We can now do a scatter plot of those data. What this scatter plot does is looking at the run ratio log and the win ratio log, and that's a new scatter plot. That looks a little bit more linear, and when I look at 0, 0, it's right about where the cursor is, the arrow tip of the cursor. That's 0, 0. And that zero might be a zero intercept, but it looks like a much straighter line. Let's get that line of best fit. And the way we do that is by running a linear model. So again, we can go to help, look at LM, the function. It fits a linear model, and we're going to compare the win ratio log to the run ratio log. Let's do that. Run that code. And here is the exponent. Nice. So for all the data from 1901, the best fit line has a slope of 1.86. 1.863. The 1.863 slope of that line now becomes the exponent in our Bill-James Pythagorean formula. And we can use either form of the Pythagorean formula, the wins-loss ratio, or the standard formula that sabermetricians know about. Let's run this again, and we will run it with a 0 intercept to see if things change. Strictly, we should run it without the 0 intercept, but for completeness sake, let's just run this. We'll have it there in the code for people to run. Slope is still the same as it was before, 1.863. So because earlier when I scroll up, the intercept is really close to 0, and we saw that on the scatter plot. We can look at the plot and see that it's really close to 0. And then when we made it 0, we can see we got the same exponent. Now if I change the data set, if I look at the dead ball era or the live ball era or the power era of the 90s and early 2000s, if I look at these different eras, maybe I get a different slope. The point is we can determine very precisely the best exponent for the Bill-James Pythagorean theorem with this technique. So now you have this code. If you need to ever run this again, we'll send this code along with the videos as you learn this lesson.